Hi folks, let's do a little math. Well, math never hurt anybody. Look at this integral. Okay, we got an a there, but that's not a variable. I left out my dx. That tells you what variable is in the problem, and that is x in this case. A is just a constant. They're telling us that it's greater than 0. That'll come up in a little bit. Well, we've got the square root. We're going to do a u substitution, and might as well pick this stuff inside the square root. Looking ahead, you see that the derivative of x squared is 2x, and we do have that x out in front, so that's a good sign. The derivative here will be 2x dx. Remember, the derivative of a squared is 0 because a is just a constant. It might as well be a 7. Let's substitute here. I've got square root of u by design. Then I've still got the x dx to substitute for. I can find that right here. X dx is 1/2 du. So I'll put that in. Let's account for the bounds of the integral. When x is going from 0 to a, so when x equals 0, u equals, I'm plugging in x equals 0, so I get u equals a squared. When x equals a, I get u equals 2a squared, because I put in a in here. I have a squared plus a squared is 2a squared. So these are the bounds for my new integral, a squared to 2a squared. And I'm ready to go. The integral is 1/2. The antiderivative of root u is u to the 1/2 power plus 1, which gives me 3/2. Then I divide by that very 3/2, but that's the same as multiplying by its reciprocal, which is 2/3. Okay, let's do a little housekeeping. That gives me 1/3 on the outside, and then when I plug in the 2a squared, you can even just do it mechanically at first, and then write down, then clean it up. Then I put the a squared in, so I have a squared to the 3/2. Okay, let's deal with this. So remember, the 2 in the denominator means take the square root, and this is an a squared. So I'm going to take the square root, that's for the 2, and then the 3 means cube it. So that 2 is going to, you can either think of it as root 8 or 2 root 2, but the 2 is to the 3/2 power, so it's root 2 cubed, and that's 2 root 2. And then the a, I'm going to take the square root of a squared, and that's when I get a, but then I have to cube it also, because there's a cube and there's a square root in that exponent. So I'll get a cubed. And this is where we use that a is equal to 0, or a is greater than 0, because when we take the square root of a squared, let's say a squared was 4, we wouldn't know if that came from -2 times -2 or 2 times 2. So when we're taking the square root, we we know which one it is. All right, minus. Okay, and then over here, we're going to take the square root, but it's a squared, so I just get a, and then I have to cube it, so I get a cubed. All right, so all told, I can bring an a cubed out in front. A cubed over 3 times 2 root 2 minus 1. That's our final answer. Number 66 is one of those ones where you see that negative pi over 3 to pi over 3. That's very symmetric. It means we have the same distance on the left of 0 as we do on the right. And the function inside the integral is this function, which if you tried to do that using u substitution, you'd get stuck and wouldn't be able to do it. So the only way to do this is to know what they're intending here, and that is for you to notice that this is an odd function. Or hope that it's an odd function, because then what happens is you can say the answer is 0. So what's going on here is in an odd function situation, it's symmetric about the origin. So when you're calculating an integral, that calculates the net area, and if you have the same distance on the right as the left, then you'll have the same area, but they'll be opposite signs, and when you do the net area, you end up with net area 0. So the answer is 0. We know the answer, but one thing, in order to get full credit for something like this, you have to actually show that it's an odd function. You can't just say, well, geez, last time I saw that there was the same number here as there, where there was a minus. The answer was 0, so I'll just say it's 0 and not really know why, but still get it right. Maybe you get a point or something on an exam like that. But the design is for you to practice showing that f of x equals x to the 4th sine x is an odd function. That's the design here. Give you that practice. Okay, so what is it we have to show? We have to show, because this is what's true of all odd functions, that when you plug in negative x, what you get is f of x with a minus out in front. So let's see that here. If I plug in f of negative x, I get that right there, that length. That would be f of negative x. And what the odd function is saying is that if you go over to x and plug it in and get that length, f of negative x is equal to the negative of this length here. This is f of x, that length. And then that's f of negative x down here. I don't really want to write all that out, but you see how this is the negative of this. That's what this is saying. So if I plug in the function here, I get the negative of this length. That's a math way of saying that it's symmetric about the origin. So we can check that for this one. So f of negative x, that's negative x to the 4th sine of negative x. Negative x to the 4th is just x to the 4th, because negative 1 to the 4th is 1. And sine of negative x, well, that's negative sine of x, because sine itself is an odd function. And to see that, we can check the unit circle real quick. If this is my angle x, then this little distance here is the sine of x. And then if I go negative x, then I get negative the sine of x. So you see how sine of negative x, this length right here, is negative of this length right here. So that's, you maybe remember that identity, or you forgot it, or you never knew it, but that's the design of the problem for you to know that about sine x. So I can pull the minus out in front, and I get negative x to the 4th sine of x, and that's negative, that's f of negative x, and guess what? That's negative f of x. So I have shown what it is I was supposed to show. Okay, so that means that x to the 4th sine x is odd, and that means that the integral from negative pi over 3 to pi over 3 of x to the 4th sine x is 0, for the reasons I was stating earlier. That you have the same area on the left as the right, but one's negative, so the net area is 0. Moving on, number 67. Integral 1 to 2 of x root x minus 1. Well, this is going to be one of those little tricky ones. It's a little bit more of an advanced u substitution. By now, if you're on number 67, hopefully you're in the habit of picking the stuff inside of the square root as your u. You'll be a little disappointed when you see that all you get is dx for du. So when we go to substitute here, I have root u by design, because I just picked u to be x minus 1. Then the dx is du, and I have this pesky x left over that I can't substitute for, and I don't see it right here. Usually I get it from this line. But instead, we'll go get it from this line. X is equal to, well, it's u plus 1. So I'm going to put that in. And now I've made my substitution. U plus 1. Okay, now we got to put the bounds in. So when x equals 1, this one right here, I'm going to plug it in to this x. I get u equals 0. Put that in for the bound for u, the lower bound. Then when x equals 2, we have u equals, put it in for x right here. I get 2 minus 1, u is 1. So those are my bounds. The integral that I'm going to do is really this integral, u to the 3/2 plus u to the 1/2. I'm just getting it ready for doing the power rule where I add to the exponent. The reason it's u to the 3/2 is because this u here is u to the 1/2, and then I'm multiplying it through here, and I multiply by this u, so the two of them together add, and you get u to the 3/2. Okay, let's do this. When I integrate, I get u to the 5/2 divided by that very 5/2, but I think I would rather multiply by the reciprocal, because having a fraction in the denominator is the same as multiplying by its reciprocal. Then over here I get u to the 3/2. I'm adding 1 to the 1/2. That's the same as adding 2 over 2. So that gives me u to the 3/2. I divide by that very 3/2, but I would rather multiply by the reciprocal. Then I'm going to evaluate that from 0 to 1. So when I plug in 1, I get 2/5 plus 2/3. When I plug in 0, I get 0 plus 0. Okay, so now we get to do some old-fashioned fractions. Looks like my common denominator here should be 15. This one will become 6 over 15, multiplying top and bottom by 3. This one will become 10 over 15, multiplying top and bottom by 5. And now I have 16 over 15, which is my final answer. Okay. Number 68 is a similar type question. Let me fix my 8. Pretty ugly. Similar in that you have to do that slightly different substitution. Here they even confuse the enemy a little more by putting it in the denominator, the square root that is. Okay, so I've got x, and then I have square root of 1 plus 2x in the denominator. My natural instinct is to pick u to be the stuff inside the square root. When I do so, I get du is equal to 2 dx. When I go to convert this integral into u, I have root u in the denominator by design. And then dx is 1/2 du, so I can substitute for that dx. But I still have this pesky x left over, just like in the last problem, and I'm going to have to solve for it here. X is equal to, I'm going to first bring the 1 over to the other side and get u minus 1, and then I'm going to divide by 2, so I get 1/2 times u minus 1. Okay, that's the conversion. Let's also convert the bounds. When x equals 0, I'm plugging in 0 for x here, and I get u equals 1. When x equals 4, I plug in the 4 for x right here. I get 1 plus 8 is 9 for u. So the bounds for this integral are going to be 1 to 9. Okay, I think I should do a little housekeeping here before we start integrating. So I'm going to pull the 1/2 out in front here. I have 1/4 out in front, still 1 to 9. And then I'm going to think of this as u over root u minus 1 over root u. And then this one here is, u is like root u, and root u is on the bottom, so they cancel. So this one here is really just root u. And I have minus 1 over root u. That's the integral that I'm going to attempt to do. I don't want a squiggle there. I want a bracket. Okay. The antiderivative of root u is u to the 3/2 divided by that very 3/2, but I'm going to multiply by 2/3 because that's the reciprocal of 3/2. Minus, now this one here is u to the negative 1/2. So when I add 1 to that, I get u to the 1/2. Then I divide by that 1/2, which is really the same as multiplying by 2. So the antiderivative of 1 over root u is 2 root u, and I recommend you memorize that. I've said that in previous videos, but I'll continue to say it because it's a good one to just have ready, and as is this one. If you watch my videos, you see how many times we're doing this. You probably get sick of me saying the same things, but I don't know that everybody's watching all the videos, so I do have to say it every time. Okay, anyway, my bounds are from 1 to 9. Now, what I'm going to do here is they both have a 2, both this term and this term have a 2 in it, but I'm going to pull a 2/3 out in front just so I don't have any fractions, because if I don't pull the 1/3 out here, I'm going to have a fraction. So I'm going to get it all out. I'm going to pull 2/3 out, and look what happens. So the 2 cancels with the 4, and I get a 2 in the denominator, but then I also have the 1/3, so it's going to be a 6. Okay, and then on the inside, I have u to the 3/2, and then over here, I have to have, see, I pulled the 3 out of the denominator, so I have to have a 3 root u here. And you might be saying, well, I wouldn't have done that. Well, you probably wouldn't have, and that's okay. The reason I'm doing it is because I've done it a few times already, and it's just easier with the fractions if I do it that way. So it's really because I've prepared this ahead of time that I do it that way, not because that's the way I think. I didn't do it this way the first time, but I like it this way just to present the final answer. Okay, now I'm going to put the bounds in. So I have 1/6 times, okay, when I put the 9 in here, this 2 is a square root, so that makes it a 3, and then I'm going to cube it. That's that 3 there, so that gives me 27. So again, square root of 9 is 3, but then I cube that and I get 27. Then I plug in the 9 here. The square root of 9 is 3, so I have 3 times 3 is 9. That takes care of the 9. And don't forget to put a parentheses when you're doing the second one. It's often easy to forget to put parentheses around the whole thing. When I put in the 1, I get 1 minus 3. Okay, now I have 1/6. This here gives me 18. And then over here I have plus 2. So overall I get times 20. And then my final answer is 10 over 3. See if you believe that. And go reproduce it yourself. Okay, that was number 68. Uh-oh. Didn't want that. Okay. That was number 68. So this is 69. This is a red problem. And the reason is because it's got that L in there. They really want you to remember these types of integrals. And it is a good idea because it's a real easy one to create for exams. And there's a wide variety of integrals that you can get from this, especially once you get into the integration by parts. Okay, this is from e to the fourth. Now when I look at this, I have over x left over, and I've got it right here. That's equal to du, so it's a perfect substitution. Let's do the bounds. When x, the lower bound is 1, when x equals e to the fourth, u equals ln e to the fourth. But before you put your, get your calculator out for that, remember we have this exponent rule. I just did this integral. The antiderivative of 1 over root u is 2 root u, evaluated from 1 to 4. And then I get 2 times 2 minus 2 times 1, which is 2. That wasn't too bad. Well, go reproduce that yourself if you are so inclined. Number 70. They're really trying to construct these things. I don't know if this would ever appear in nature or anything. I mean, when you're trying to study nature, do we get integrals like this? I don't know. But here we have sine inverse x divided by square root of 1 minus x squared. The observant student will see that 1 minus x squared inside of a square root, well, that's the derivative of inverse sine. So a great choice for you here would be, how about u equals inverse sine? Then du is, well, it's 1 over square root of 1 minus x squared dx, which is exactly what I'll have left over after I make the substitution. So we've got u here because u is this, that's the u, and then what I have left over is the dx over square root of 1 minus x squared, and that's exactly du. So look what I have there. I have u du. That's a pretty good integral. I can do that one. Let's do the bounds. When x equals 0, see, now you got to know your inverse sines. Okay, then u equals inverse sine of 0. Okay, well, what's that? So it's not sine of 0, it's inverse sine. So the way you handle that is you say, what angle is sine at 0? What angle is sine 0? What is the angle where sine is 0? Because sine takes an angle and gives a number. Sine inverse takes a number and gives an angle. So it's saying, what angle is sine equal to 0? And the answer is 0. Okay, so when x is 0, u is 0. All right, how about when x equals 1/2? Well, then u is going to be sine inverse of 1/2. And then you ask the question, what angle is sine 1/2? You can look at a little unit circle here. So the sine is the vertical component. So that's, if it's short, then it's going to be the 1/2. And where does that happen? That happens at pi over 6, 30 degrees. So sine of pi over 6 is 1/2. So the angle where sine is 1/2 is pi over 6. See, inverse sine. Sine takes an angle like pi over 6 and gives you out 1/2. Sine inverse takes 1/2 and gives you the angle where sine is 1/2. Okay, so u is pi over 6. And now we're ready to go. Okay, the antiderivative is u squared over 2. We're going to evaluate that from 0 to pi over 6. When I put in pi over 6, I get pi over 6 squared over 2. And we can do a little housekeeping. We get a pi squared, and then we get a 36. But So it's pi over 36, pi squared over 36 over 2. The way to get out of this jam when you have fractions within fractions is multiply top and bottom by one of the denominators. Okay, so there it cancels, and on the bottom I end up pi squared over 72. And we have minus 0. I didn't put the minus 0, but that's 0. Number 71. Number 71. Integral 0 to 1 e to the z plus 1 over e to the z plus z dz. Well, this is a 1 over u du. You see how this guy here, the derivative of it is e to the z plus 1, which is exactly what I have up there. Now, you might not just jump right to that answer. You might play around with it for a little bit, maybe even break it up into two fractions. But that is the way to go here is pick the whole denominator to be u. Then du is e to the z plus 1 dz. When I go to convert this integral, I have u in the denominator by design. And then what do I have left over to substitute for? I have e to the z plus 1 times dz. That's exactly what I have right here. So I have du there. That's 1 over u du. And then let's do the bounds. Okay, when z equals 0, I'm plugging 0 in right here. I get e to the, so u equals e to the 0 plus 0, which is 1. Don't just ignore that. You know, the e to the 0 is 1, it's not 0. Okay, then when z equals 1, u is equal to e plus 1. Okay. Well, the integral part's not too bad. That's ln absolute value of u evaluated from 1 to e plus 1. And then I plug them in. I get ln of e plus 1 minus ln of 1. This is 0. And then we don't have to have the absolute value for this because e plus 1 is a positive number. Okay, so there's your answer, ln e plus 1.